Cool. So I think we're ready to get started. So Dr. Bilodeau is going to finish last time's lectures, and then we're going to transition into Dr. Yue, who will be talking more about dimensional reduction, which is a necessary step to start looking at variational autoencoding to look at generative methods for molecular design. So let's go ahead and get started with that. Thanks,
Cool.
everybody.
Let me start by sharing my screen. Okay, so to start, I want to remind everyone that setting up the GCNN notebook takes a really long time. And so if you haven't already, please open that up. I'm realizing I opened it up yesterday, and now that I'm restarting the notebook, I have to reset this up. There might have been a better way to do this, but I don't know what it is. So right now this is setting up. And so I was thinking while we get this set up, I'll start presenting the information I was planning to share to you about kind of more practical elements about how to train a neural network. And if we have this pip install thing going on in the background, hopefully by the time we finish with the slides, we will be ready to finish the notebook. So if you haven't already, get this opened, get this installing so that when we get to the notebook part, we can all kind of like work through it together. Okay, so I'm going to move this out of the way. And cool. Okay, so welcome to day 4. Today, predominantly what I want to talk about in these slides is some of the things we sort of started to touch upon in response to some of the questions that were being asked yesterday, which are largely around, how do we know whether a model is doing well, and how do we know what the best way to train our model is, and this sort of thing. So basically, how do we evaluate model performance, and what does it mean for a model to perform well? So starting with this kind of thesis question, how do we know whether a model is doing well? So I think it's an important thing to recognize the only way that we can evaluate our model is generally using some sort of test set performance. And so why is this important? Well, what we are ultimately desiring to know is, first, we want to know how closely our model approximates some sort of ground truth function. So we're basically saying that there exists some ground truth function that relates our inputs to our outputs, and we're trying to basically find the weights that correspond to that ground truth function. But also, second, we want to know how well our model will perform when it's deployed for real-world problems. And the reason I'm breaking it out into these two separate objectives is because there are many times when maybe this first objective of identifying this ground truth function is maybe too difficult, and we're sort of settling for the latter. And so what I mean by that is sometimes we don't actually have enough information to predict our output from our input. So as an example, if we're trying to, for example, predict the viscosity of a solvent and our input data has been taken at multiple temperatures, if we don't provide that temperature as an input, obviously there doesn't necessarily exist a direct relationship between our input and our output. And so that temperature variation is going to lead to effectively just error. And so ultimately our goal is to learn this ground truth function, but there can be challenges associated with that. And so when we kind of ask how we want to know how well our model will perform when deployed for real world problems, in kind of stating this, we're maybe saying that we know our model doesn't necessarily work perfect under all circumstances. We maybe know our model doesn't necessarily know this ground truth function. Maybe we make peace with that, but our goal is instead to evaluate how well our model performs under certain kind of test case scenarios that we would like to be able to use it in order for our model to be useful. So for example, if I know my model doesn't generalize well in chemical space, but it only works on maybe some set of molecules, I could say, oh, well, that sucks. My model should be better. Or there might be some use case scenario where it is actually okay for my model not to generalize to all possible molecules, but instead to work really well on some subset of molecules. And so this is kind of what I'm attempting to capture in this second bullet point. Okay, so where does model error come from? So this was in kind of something that I answered in response to a question yesterday, but I wanted to break this question out a little bit more systematically. There are a number of different potential causes for error. So the first one is that maybe our ground truth function exists and it can be represented with our neural network, meaning that H layer or whatever our architecture is expressive enough to represent the function, but we just can't find the weights. And so that can be for a couple of different reasons. First, our optimization scheme might not be sufficient to arrive at the global loss optimum. And so this is purely an optimization problem. Second, we might not have enough training data to constrain our optimizer. And so this is that idea that our signal is really coming from the loss. And so if our loss function isn't giving enough signal to get to the global loss minimum actually corresponding to your ground truth, you might not be able to find your ground truth. And then finally, depending on your problem, your training data itself might have too much uncertainty or noise to constrain the optimizer. So this is this idea that maybe you have a lot of training data, but if you imagine that each of your training data points has some Gaussian noise associated with it, then again, finding the global minimum of your loss function, even if you're able to do that, which again, you might not be able to because your optimizer can't find it, but even if you are able to, that minimum, if your data has too much noise associated with it, might not actually get you to the ground truth function. And so these are kind of scenarios where, again, there exists a ground truth function and your model is expressive enough, but you still can't get there because of these optimization challenges. Second, the ground truth function may not be represented within your neural network. And so this can exist under kind of maybe two categories. First, a larger and or different architecture is required to represent the function. And so this is this idea where perhaps your neural network isn't big enough, and so your function is really complex. But if you have too low dimensionality, you may not be able to represent your function. But also, especially as we move away from fully connected networks to potentially other types of architectures, we described the idea of like graph neural networks, for example, as being kind of like neural networks except where maybe we're imposing certain structure on our inputs. And we're saying we're going to, instead of having all possible nodes be related to all possible other nodes, we're going to say that there are specific relationships between nodes. And by constraining the relationships, we're actually maybe better able to learn our function. But if those constraints are inappropriately chosen, for example, maybe, if I assume in the example of a molecule that, the covalent bonds are what tell us whether or not two atoms can talk to each other. But if there are many, many intramolecular hydrogen bonds, for example, that might be a scenario where actually the way that my model is propagating information implies that covalent bonds are more important. And so maybe there's important information that's missing that prevents my architecture from really capturing important information. A second scenario, though, within this is that maybe our ground truth function doesn't exist. And so I kind of got ahead of myself before a little in saying this, but this is the kind of scenario where maybe we actually are not providing our model enough information for it actually to be able to map our inputs to our outputs. And I think this is worth flagging because I do think this happens a lot, right? Especially because if you're using experimental data sets, you could be in a scenario, for example, where not enough information was actually recorded about the experiment. And some of that information plays a critical role in kind of the outcome of the experiment. And so if that information is not being provided to the neural network, it's just not on, it doesn't have enough information to actually be able to predict that outcome accurately. And so again, temperature and viscosity maybe being a good example of that. If you're taking the viscosity measurements and you didn't temperature control your room, and some of them were taken in the summer and some of them were taken in the winter, you can get this entire source of variability that is maybe not actually available to your model, and so your model can't possibly make accurate predictions. And then finally, the third scenario I want to highlight is that maybe our test set has too much uncertainty and that this is preventing us from knowing whether or not we've found the ground truth function. And so this gets back to what, I was saying on the previous slide, which is that our entire ability to evaluate our model kind of boils down to a test set at some point, this held out set that evaluates model performance. And so if that set itself has a huge amount of like Gaussian error over it, for example, then our model may have actually found the ground truth function, but because the only lens through which we can actually evaluate our model is kind of beholden to this test set, we may not be able to actually see that we've found the ground truth function, because if our model is perfect, but our actual data is imperfect, then we're still going to get a bad parity plot, right? Maybe another example of this is a scenario where maybe we have a very small a small test set or non-diverse test set that is not super representative. And so this can again be a scenario where maybe like our entire ability to evaluate our data might be colored by model performance on a handful of samples. And so this kind of illustrates how this question of how good is our model can actually be quite a lot more complex than just looking at an R-squared value or looking at a mean squared error value. To add a little further depth to this, again, if we say that our entire ability to evaluate our model comes down to the test set, well, then the question might arise, well, how do you decide what your test set should be? And so for a lot of standard, at least deep learning training applications, we would want to split our data into a training, a validation, and a test set. And so just to give kind of some standard splits, I would often split into 80%, 10%, 10% in each of these, although this definitely varies by applications. It depends on how much data you have, how your data is distributed, etc. And so here the training set is defined as the set in which we're going to use to directly update model weights. And so this is literally going to be the data set we use to calculate our losses and do backpropagation. Our validation set is the data set we're using to make hyperparameter choices, architecture choices, and these types of things. And so in this sense, our validation set we're using to evaluate performance, but we're then going to use that performance information to then go back and make model design choices. And then our test set is going to be a held out data set, which must be separated from the validation set and is going to be used to finally evaluate our model and give us some information about how well we can expect our model to generalize on new data. And so an important aspect of this is because in deep learning training, we have so many hyperparameter choices, so many architecture choices. And I think this was really underscored by some of the discussion we were having yesterday. The validation set in and of itself is not a good overall final metric of how good we can expect our model to perform on unseen data because we're using it to make model decisions and model choices. And so even though it's not being directly used to update our weights, it is being used directly to evaluate hyperparameters. And so in some sense, we are fitting our hyperparameters to the validation set. And so often what we'll see is that our model will perform best on the training set, a little worse on the validation set, and then a little worse on the test set. Now, depending on your data set size, if your 10% splits are fairly small, we can wind up with situations where just by pure chance of where molecules go, we end up with better performance on validation or test than on one of the other categories. But in general, we would expect that training is best, validation performance is a little worse, and then test is a little bit worse. It's also important as you think about reading papers and seeing other people's slides and stuff, to make sure that you always are keeping in mind, like if their model looks really good, are they telling you about their training set or their test set? So just a thing to keep in mind, and also to keep in mind as you present results. So now we kind of have a sense of how data can break down between these, but another question might be, well, how do we decide which samples will go in each data set? So a very standard way of doing this would just be to do random sampling. So if I have 1,000 data points, I'm going to just randomly assign maybe 800 to training, 100 to validation, and 100 to test. And I think when in doubt, this is probably, in my opinion, the best way to do this. However, there are a number of other ways, and here I'm kind of highlighting two. One technique is called scaffold or chemistry-based scaffolding. Um, and so the idea here is that if you have a molecular data set, so typically this would be a data set with small molecules, you might have some sort of algorithm that tries to identify common chemistry scaffolds within each of these molecules. One common algorithm is the Bemis-Merco method. Um, and so in this, basically what you would do is you'd say, okay, I want my model to be able to learn on one set of scaffolds and then extrapolate to another scaffold. And so this is an inherently more challenging like scenario than random sampling because it means that we're expecting a higher level of generalizability from our model. And so in doing that, you'd basically incorporate that into your splitting procedure where you're basically saying, I'm going to hold a set of scaffolds in training and then put another set of scaffolds in validation and another set of scaffolds in test. And so be evaluating my model's ability to generalize across scaffolds. Another type of splitting is called temporal sampling. And so traditionally, temporal sampling is something that is used, especially when we might be training our data on large historical data sets that have come from experiments that were maybe conducted over many, many decades. So, for example, in the pharmaceutical industry, pharmaceutical companies might have data sets where, they have, certain screens were conducted 10 years ago, 20 years ago, 30 years ago, and through electronic lab notebooks and other types of kind of databases, they've kind of combined all of this information. But over that time, there's potentially small little things that change over time, right? Procedures change, equipment changes, there's updates, and not all of that information might be captured experimentally. And so even though all that data might be trained in the same model, a lot of the times there might be kind of small differences between data that was collected 20 years ago and data that was collected 10 years ago versus data collected today. And so to account for that, what folks will often do is they'll train on an older data set, and then they'll validate on slightly newer data and then test on the newest data with the goal of specifically testing whether or not your model can generalize from older data to new data. And then the reason, again, being if I kind of go back to this second bullet point here, if our goal is to evaluate how well our model will perform when deployed for the real world problem that we're interested in, what we want to do is basically design splitting strategically to recreate the scenario we want our model to perform in. And so if the scenario is, I want to train on data today, collected today, in order to predict an experiment happening tomorrow, then this temporal split makes a lot of sense, right? We're trying to train on old data because ultimately where we want to be able to generalize it is to new data. Another way to think about temporal sampling, so I guess that's a common sampling technique in the pharmaceutical industry, but I think it's worth thinking also about, you could probably apply something similar conceptually if you were doing training on models from sequence data. And so if we're thinking about training, for example, on molecular dynamics simulations, one could probably conceive of like a similar scheme associated with molecular dynamics simulations where maybe you do splitting along kind of time points and kind of can come up with something, almost box averaging related. But I won't go into that because I don't know much about that and I don't really have any basis for that. That's something I'm just thinking of as I see this. Another category of splitting I want to highlight is a subclass of splitting called combinatorial data splitting. And so I want to highlight this because I think there are a decent number of situations where instead of trying to predict the properties of one molecule, you might be interested in trying to predict the properties of a mixture of molecules or a pair of molecules. Or maybe instead of one material, you're trying to predict the properties of maybe composite materials, right? And so in doing this, it's worth noting that this random splitting strategy that I said was a good idea or good kind of first pass is not really very good for combinatorial data sets. And so to illustrate this, I want to highlight a project that I worked on as a postdoc. So basically, the problem that I was interested in was predicting the viscosity of mixtures of liquids. And so I had as an input two smiles, a mole fraction, and a temperature. And what I wanted to output was viscosity and uncertainty. And so an important element here is that I wasn't training on just one molecule, but instead I was training on two molecules. And so instead of and so if I look at this entire data set, I could have a scenario where maybe I have, thousands and thousands, like 30,000 data points, but where many of those data points share one of the mixture components, right? And so all of these data points are not necessarily independent of one another, but are rather linked by the fact that we have many different combinations of shared data points. And so in order to do splitting, I didn't necessarily just randomly split, but instead I kind of came up with these different use case scenarios. So one was where I'm trying to make a prediction about a new mole fraction, but where both molecules are already present in the training set. And so this is the idea that the model has been trained on a pair of molecules, but maybe I'm trying to make a prediction about a new, like a new mole fraction. Another scenario is one molecule is present in the training set and the other is not. So maybe, for example, I've trained on many examples. I think yesterday I used the example of, I have many training examples of water with varying other solvents, but I have another solvent that's new. And so I'm trying to predict the viscosity of this new solvent mixed with water, even though my model has never seen that new solvent. And then the final scenario is where neither molecule in the mixture was present in the training set. And so you can think of this as this is the maybe easiest scenario, right? This is really just interpolation. So we probably don't even need a neural network to do this. This is maybe a more difficult scenario where we're really actually utilizing, we need this graph neural network to learn something about this new molecule that hasn't been seen in training. And then this is the hardest scenario where I'm trying to predict the properties of a mixture, which is completely unseen to my model. And so in this case, I created a scenario where I had really two types of test sets, one which I called the partly held out test set, which corresponded to this scenario, one which I called the fully held out test set, which corresponded to this scenario. And I made sure I did not have any scenarios that looked like this in testing. If a pair of molecules existed in the data set, I put all of the data into training or I did not. And so in this way, I basically constructed something that's going to be, I expect to be more difficult than just kind of random splitting, where I'm likely to have most of my mixtures being present in the training set. And again, the reason for this being, I want to be able to ensure that what I'm evaluating is my model's ability to predict these kinds of scenarios, right? If someone dreams up a new solvent, can I actually predict the viscosity of that mixture? And so I wanted to highlight this because this is pretty critical to being able to predict any combinatorial data. You could also think about data like if you're trying to design a catalyst and like a substrate or something like that pair. Really any data where you have two molecular inputs instead of one, you'll need to think about how to think about splitting strategically. And so I guess maybe to kind of say this in more general terms, more complex data strategies are needed really anytime your data set contains non-independent data. So I guess, you can sit and think about whether your data is like independently distributed. And if it's not, you should think about whether you should come up with a new splitting strategy that does a better job of telling you whether or not you can generalize. And so kind of, I guess, reiterating the thing I keep saying over and over and over again, it is not that impressive to get a really high R-squared score or a really low MAE in general, because it's important to recognize the relationship that those metrics have to things like splitting and to things like, your data set sizes and things like this, right? The real way that we care about these metrics is in terms of their ability to tell us about how our model will perform under a specific scenario. And so there are lots and lots of times where you'll see a model that seems really good. And then if you actually think about how it would actually apply to the real scenario, it's really not, the study has not been designed in a way that tests the important question. So that's my soapbox. Okay, so another thing we talked about yesterday was data balancing. And so I wanted to talk about this briefly. So the idea behind data balancing is that balanced data sets are really required for learning functions in an unbiased way. And so a common example of this is maybe learning cats and dogs. If you have 100 examples of dogs and 900 examples of cats, your model is very likely to assume that the next thing you show it is going to be a cat. But another example is in facial recognition. There was a model that was developed many years ago now in like 2015 that was intended to try to predict, given a face, whether or not that face was smiling or frowning. And then but one of the biases in that data set was that in the original data set, they found that this was the like pictures of celebrities or something, celeb data set. And so it turned out that in that data set, women were far more likely to smile and men were far more likely to frown. And so when it saw a picture of a man, even if that man was smiling, it was more likely to predict that man as smiling instead of frowning, just because it had this built-in bias that men frown and women smile. So I thought that was funny. You can do what you want with that information. But at any rate, so it's important to recognize that data balancing should be considered with respect to both the input and output representations of the data. So the idea here being that you can have imbalance in terms of the like attributes of the data. So in this case, men versus women might be an attribute of the input data. And then smiling versus non-smiling is an attribute of kind of the output data. So in one case, maybe input data belongs to several discrete classes. And so this would be a scenario where then you might need to think about whether or not there's imbalances in those classes and whether or not your model is naturally inclined toward being dominated by one of those classes. But then on the reverse side, you can envision a scenario where maybe, especially in classification problems, where you have an imbalance in positives or negatives. And so some strategies in deep learning for dealing with an imbalanced data set are things like oversampling. So this is where maybe you basically artificially create more examples of one type of data in order to basically overemphasize that data. So this would require some sort of augmentation strategy. Undersampling basically means you're just going to randomly remove some members or some data associated with the oversampled class. And then weighting is basically where you're going into your loss function and literally saying, okay, some of this data should impact my loss, should have a bigger weight in terms of backpropagation than others. Okay. And then a final scenario is that maybe the variable that you're predicting follows a skewed distribution. And so I'm sorry, I realized I put a lot of examples from my viscosity paper. So, but an example here is that in this particular instance, the original distribution of viscosity in this data set was very skewed in the sense that there's a lot of data at relatively low viscosity, so around 1 centipoise, and even below that, and there was relatively low amounts of viscosity data at these high viscosities. And so to make this a more kind of Gaussian distributed data set, and then honestly, anyone who has performed this prediction before me has also done this. It is very common in machine learning of viscosity data sets to perform a log transform so that you're not predicting the viscosity, but rather predicting the log viscosity. And so this prevents the kind of overemphasis of the low end of this data set. Okay. And then one final thing I want to highlight, maybe before we go on to the notebook, but I won't spend too much time on this, is that regularization is a tool that we can use to avoid overfitting. So one strategy that we can employ in order to reduce overfitting is this early stopping. And so this is basically where we just look for the point at which the validation set stops improving and we stop there. Another technique is dropout. And so this is a technique where we can randomly remove certain nodes during training with a specific probability, and we'll scale the outputs so that the magnitudes of the latent vectors don't get affected. But ultimately what this does is it forces the neural network to kind of learn a bit more of a condensed representation of your input in terms of predicting your output. And so it kind of prevents overfitting in this fashion. And so there's a relatively straightforward way to implement this in PyTorch. It's basically just you can add like a dropout layer in PyTorch. And then there are these techniques, L1 and L2 regularization, which update the cost function to penalize non-zero weight values. And so again, similar to dropout, this is going to drive some of the weights to zero in order to try to make sure that your model doesn't use more weights than are necessary to represent your function. Okay, cool. Hopefully at this point, my GCNN notebook is gonna work. I'm just gonna quickly test it. And that looks like it works. I'm just gonna jump down and test this part just to make sure that everything. Cool, all right. So let me make sure that I run all these things from before. I don't think I need that. Phone. Working. All right. So last time we had defined this new PyTorch geometric type of data set for molecular graphs. And then we had also defined this graph neural network class, again, based off of leveraging this GCN conf PyTorch geometric layer type. And I think I mentioned last time, but if you're interested in exploring other types of graph convolutional layers, they totally exist. There's a lot of different ones that have advantages and disadvantages that you can explore, and they're fairly straightforward to use in PyTorch geometric. All you would do is import, another name and then replace this here. So then to pull this all together, we're going to need to import our data loader from PyTorch Geometric. And so, as I mentioned a few times yesterday, a key challenge with training neural networks on graphs is that now our inputs have different sizes, right? Because we can have different numbers of atoms, they can have different connectivity. And so the main challenge with that is that it just kind of messes up a lot of PyTorch's built-in batch handling. And so the PyTorch geometric data loader works differently than the regular PyTorch one because it handles batching differently. So we're going to use the PyTorch geometric data loader. We will define our device, place our model on the device. So in this case, this is CPU, but if you are using a GPU, you can replace that. We'll define our data loader, set our batch size to 32, and set our optimizer, and set our loss function. Hmm. think I'm going to switch this to lipo smiles because I think this is maybe an issue with the data set that I've chosen. So let's go back to the lipophilicity data set. I'm going to redefine these things and hopefully there are some quirks to the particular aqueous solubility data set that I chose just there. So apologies for that. Happy to talk more about that if you're interested, but the bottom line is they're kind of ugly smiles. Okay, so with that, now it looks like our model has been able to create this data set. As we talked about before, our data is going to be stored in this data.pt. And so that way it's kind of already done this processing where we're turning our smiles into an RD-kit molecule. And from that RD-kit molecule, we're constructing our molecular graph and then turning that into a PyTorch geometric graph. And so that's being handled here. And then it's also being handled up here using these utilities that we've created. And so with that, hopefully I can train my model. So now just to kind of reiterate what we had talked about yesterday, overall, this model training is going to look really similar. What I'll do is I'll start by setting my model to train. I loop over my epochs. And then I'm going to loop over my batches. I set my optimizer to 0 grad. I will make my prediction. In this case, I am feeding my entire batch into my model and then getting the output, whereas I think previously I split this into X and Y. So this is a difference in how PyTorch geometric natively handles the batch data. Then I will calculate my loss, calculate my derivatives, and then perform my optimization step. Here, I have not gone to the lengths of actually constructing a training routine and a validation routine as we did last time. But if you're using this in a real application, you would potentially want to not just do this, but actually split your data into training and validation. And then, as we talked about last time, have a separate training and validation routine. So here we've kind of kept it simple, but that's just for simplicity's sake. Then while this is still training, I'll kind of show down here, I've created, just as we did for the fully connected neural network, a predict function, which basically is going to take in our model and a data loader. It'll set our model to evaluate, and I will create these lists to kind of take in our input data and our output data and our predictions. I'll set my model to torch no grad, and then I'll loop over a bunch of batches in order to make these predictions, collect them, and then return them. And so after I do this, I should be able to make predictions, get a parity plot, and an R-squared score. Cool. And this is done running. So now I'll run this. All right. So now for our parity plot. Cool. So that looks pretty bad. But as you guys remember from previously, it usually takes a fair bit more than 30 epochs to get a reasonably decent model. And so this is maybe not super surprising. So again, this is going to be true values of lipophilicity on the y-axis, or sorry, x-axis, predicted values on the y-axis. And so if this model was perfect, we would expect all of this data to lie on the y equals x line, but it doesn't. If we calculate an R-squared score, you can see that our R-squared is only about 0.086, so pretty bad. Okay, cool. So now you know how to create a graph convolutional neural network using PyTorch geometric. Maybe in the meantime, I can take any questions, and then while I answer questions or while you're entering them into the chat, you can also think about, in this case, we didn't include training or validation splits, but how would you go about actually going back and including training and validation splits? And so if you're interested in trying that during these last, 5 or so minutes, 5 to 15 minutes, I suppose, you can try and see if you can recode this to include those kinds of splits. Okay. So I'm gonna look over into the chat. Okay, and so the first question from Robert is, are there realistic situations where we encounter, oh, I'm not looking at the slides. Hold on. Let me pull the slides back up. I'm going to answer Robert's question about the data loader cells. So this is the data loader cells. And while I'm doing that, I'm going to Okay, so the question is on the sources of error slide. Are there realistic situations where we would encounter 1C and not scenario 3? So where our training data has too much uncertainty and or noise to constrain the optimizer. That's a fair question as opposed to our test set. Yeah, the only scenario I can really come up with is there have been maybe. So there might be scenarios where you are the source of data for your training and your test set might not be the same. So for example, if you are gathering training data, a lot of the times a major criteria is that you need to have a ton of data, right? So you might be going into the literature to find that data, or you might be using, for example, a high throughput experimental technique or a high throughput simulation technique to get that data. But because of that, that might be inherently error prone. But there might be a scenario where maybe what you're trying to do is use that to predict some sort of ground truth data that is maybe more accurate. So for example, if you're taking a huge bucket of experimental literature data that's kind of error prone, but then you're gonna use as a test set maybe data that has been collected by a collaborator that maybe has lower error and maybe you trust more than all of these different experimental sources. You could kind of envision a scenario where your training data has more error than your test set. So the only way I can think of is these scenarios where your training data comes from a fundamentally different source. So I don't know if that's a situation that everyone else is encountering a lot, but I do feel like I encounter this situation a lot where in order to boost my amount of data, I'm going and looking either through high throughput methods or through literature. And then because of that, I'm maybe willing to tolerate lower fidelity data in order to try to like boost performance. But then because of that, I have maybe lower fidelity data in training and not in testing. So Lesek asked the question, what are the criteria or heuristics for how many samples are needed to use neural networks models in the first place? Are there any strategies one could employ for small data sets? So yeah, it's a tricky question because I think it depends a bit on your neural network architecture. So typically, if I'm working with a small data set, I would think about whether or not there's a way to do some sort of transfer learning or some sort of, strategy that you can use to boost performance by leveraging some sort of data set that does exist that is bigger. And so what I mean by transfer learning is there are a variety of ways to think about transfer learning. You can essentially train a model on one data set and then use the weights from that trained model to initialize model training on another data set. You could freeze parts of the neural network using the weights that you obtained using the first model training. And so that would potentially allow you to train models on smaller data sets in maybe the tens to hundreds of data points kind of regime. Typically, if you're working with a data set in the kind of hundreds of data points regime, you would want to be careful about how big, how many weights you have. So, for example, thinking about, hidden dimensions on the order of tens of neurons instead of hundreds of neurons. And then usually an ideal situation for most neural network applications, we would want to see that you have on the order of more like at least low thousands of data points is like a typical neural network application. So if you read a lot of like deep learning papers, and you look at like the molecule net benchmarks, most of the benchmarks at kind of a minimum have like low thousands of data points. So that's not necessarily a hard and fast rule by any means. I think the kind of rule of thumb is try it, it might work. But I think it's worth maybe noting that that seems to be where people are often employing neural networks. And I guess that also gives you a little bit of a sense of what I've seen in terms of, or what I've typically done in terms of building models for different kinds of applications. Another question from Nafis was, can we get a negative R-squared score, and what to do if we see a negative R-squared score? Yeah, you can totally get a negative R-squared score. So what an R-squared is basically telling you is it's telling you the relationship. If I go back to my parity plot, it's effectively telling you about the relationship between the spread of your data. So if I think about like here, my data might be spread from -1 to 4. And so what is the ratio of the like spread of the data here versus the spread of the data around your y equals x line? And so if there is literally more spread, or if your data points are literally further from the y equals x line than they are from the mean, then you will get a negative R-squared score, meaning you would have been better off. I guess the other way you can think about it as an R-squared score is basically capturing how much better you are doing than just giving the average, right? And so, if that R-squared score is near 1, then you're doing way better. But if your R-squared score is near 0, that basically means that that giving the mean and giving the like prediction are effectively interchangeable. You're going to get a similar amount of error. Getting a negative score effectively tells you that if you used a mean to predict your model instead of your model, then you would actually get a better prediction. So I don't know. So yeah, it can be negative, and that means your model's really bad. All right, so I think we're about time for a break, but I'm happy to stick around and answer any more questions if they pop on the chat. Otherwise, thank you for asking lots of super interesting questions. I've had a really fun time sharing neural networks. How should I start hyperparameter tuning? Yeah, so for sure, I guess I would say to start, like the dimensionality of your layers, like it's worth thinking about the dimensionality of your input, but the dimensionality of your layers can be quite a lot smaller than the dimensionality of your input. You could think about making like the first layer kind of big and then making it like kind of creating like a funneling kind of effect. Or you could just go straight from like 3000 to like 100 or 200. But it really kind of depends on what your data looks like. How much data do you have? How independently distributed is it? Because if you have a limited amount of data, I would probably always try a lower number of layers and lower kind of width layers. But then if you have really huge data sets, then it's worth potentially trying, bigger models and just seeing where that lands you. I mean, for me, in terms of just like bread and butter first pass choices, if I have a fairly large data set, like, 10,000 data points kind of data set, independently distributed data points, I might do hyperparameter searches over like, 2 through, okay, 200,000 data. Okay, so 200,000, I guess it's important to recognize independently distributed data as opposed to like connected data. Because like if you have combinatorial data and it's 200,000, then it's like, that's kind of different. But if it's independently distributed data, then yeah, like you could probably try, deeper networks and wider networks. And so what I mean by that is kind of like, on the order of like 4, 5, 6 layers, 7 layers, and then wider networks. I've never gone above 1,000, but like in the high hundreds, you could try. Just again, trying a scan. It's really like you'll always want to do hyperparameter optimization, but it's just a question of like how would you define those bounds. And so then as you're starting that hyperparameter scan, you can pretty quickly see whether or not, you've chosen correctly by also looking at those loss versus epochs. There are definitely other kind of more fancy ways of doing hyperparameter optimization, like using Bayesian optimization to do hyperparameter searches, and I'm sure they work well. I personally often tend to prefer to like watch what's going on and to try to have some manual hand in it, just because I don't know, maybe I'm kind of old school. I like to feel like I have a sense of whether or not my model is overfitting or underfitting, or kind of build an understanding of how, for a specific problem, my training process is changing with parameters. So I don't know. That's just my bias. But like, I don't know. I'm seeing you nod, Shuwen. Do you do the same thing?
I do the same. I also feel old school there, but it just feels like you have more control, otherwise it's a bit too black boxy.
Yeah, and then it also feels like you've learned, you're like, oh, I'm not going to go to like higher widths because I know what the consequence is. Whereas if you've just trusted your Bayesian optimization scheme, like you haven't like put your eyes on like the, I don't know.
Right, it's kind of like instead of getting a minima, you get a gradient, so you feel a bit more comfortable that it is in fact a minima.
That's a good way to put it. I like that.
All right, Camille, thank you very much.